Thank you. I've got a lot of slides, but mostly pictures, so I'll zip through them. Yes. Oops, I got it. Okay, that's the abstraction. All right. So, what is dilbit? Well, bitumen that's extracted in the Athabasca oil sands region is too viscous to move through pipelines. So, they have to blend this with lighter hydrocarbon fractions. And the general term for this is diluted bitumen or dilbit. There's a wide variety of types of dilbit, but I'll just use the general term dilbit. And so when this project first started, there was hardly any studies that examined the fate of dilbit because it has different physical chemical properties than regular conventional crudes, whether it's light, medium, or heavy. And there have been some studies that had taken place in the marine environment, some in the freshwater environment, but none at all in shallow groundwater systems. And there were still some research gaps in river and lake systems. For example, what is the effect of wave action weathering, and how much do microbes actually preferentially utilize dilbit to other carbon sources? So this highly innovative stuff had never been done before, and we tackled this problem. And I'll show results mostly from the first two experiments. So most of this work was, involved controlled spill experiments because there weren't any places to go and check for dilbit spills at the time. So I'll show the work that was done for the large column and large tank experiments, and I'll just show some pictures from other collaborations. So shallow groundwater systems. So these are carried out at La Beaulure here in Quebec City, which is operated by INRS. It's called the LIST facility. I forget the acronym. So here we're looking at controlled dilbit compared to conventional heavy crude, and see what we're going to examine. The geochemical, hydrogeochemical, and toxicological parameters changes over time in the BADO zone, that is the unsaturated zone. So we had two large columns that were amended with dilbit, two with conventional heavy crude, and one control. And in the soil, we examined both soil and leachate over time, over 104 days, and we measured total petroleum hydrocarbons, TPHs, phospholipid fatty acids, which are a biomarker for the active microbial population, PLFAs, and isotopic analysis, carbon 13 and carbon 14, to understand microbial incorporation of dilbit and conventional heavy crude. We looked at microbial community analysis, and in the leachate, we analyzed EOC, BTEX, benzene, toluene, and benzene xylene, pHs, polysaccharides, and hydrocarbons. These two groups here are typically considered the most toxic constituents from oil spills. That's why they were included. Acid extracted organics, which includes naphthenic acids, which are a major toxic component in bitumen. We looked at metals, and we carried out toxicity analysis on the water over time using fat and minerals. And so just these are results from the soil from looking at microbial incorporation of dilbit and conventional heavy crude carbon over time. And so dilbit and conventional heavy crude showed similar biodegradation over 104 days. There wasn't any difference between conventional heavy crude or dilbit, which is very important from an engineering and remediation perspective. So up to 20% of carbon was found in PLFAs, whether it's from CC or dilbit. And in terms of microbial community species, there is a shift to a known hydrocarbon degrader over time. Yes, so the natural attenuation potential for dilbit is similar to conventional heavy crude. So this graph shows the carbon 14 in the PLFAs over time, and you can see that there's a shift going towards the value of fossil carbon, which is minus 1,000 ml. And so in the top part of the controls, no change. Okay. So here's some results in the leachate. Here we have BTEX, and here we have pH, total pHs, so PACs. And you can see that the main spike in BTEX, which are more water soluble, was in the first few days, the first couple of weeks of the experiment, and the pHs, which are very low, tend to leach out over time. There's slightly higher concentrations of BTEX in the dilbit, cold lake blend dilbit, versus the conventional heavy crude. So here's the toxicity results from this. So you can see that there is definitely a difference between the cold lake dilbit and conventional heavy crude compared to the control. But there's no difference between the two different types of petroleum. So this is the acid extracted organics containing naphthenic acids, and here we have the control, dilbit, conventional heavy crude. And what's interesting is that over time, you have this increase in the O3S species, or the oxygen-containing sulfur species, but not in the control. What's interesting is that neither the BTEX, nor the pHs, nor the ethanic acids, nor these compounds were related to toxicity. And that's a recurring theme. Despite all the analysis to be carried out, we weren't able to determine which particular compounds were responsible for toxicity in these experiments. So here's a large tank experiment, also carried out at INRS. So we had sand from a quarry near Quebec City, and we filled this large tank up, and we made our source zone by adding about 20 liters of dilbit, 16 kilograms. We placed it in this box, and then we opened the box up. It was homogenized. We tried to minimize how much free phase there was that would bias our results. And so we created a system that had a flow of roughly 1,000 liters per day. And we created this hydraulic gradient, and we measured the leachate that was from a nest of piezometers across the tank. So I'll just show toxicity. Interesting, in the leachate that was exiting this tank, you see nothing. And then the BTEX and spikes were similar to what we found in the columns the first few days. But here we have an increase in toxic effects later on in the experiment in the dilbit. This is just on the dilbit, not conventional agriculture. So, and here we have, I'm just going to show a picture of this. This is work done in collaboration with people at CanMet Energy. And it's a similar tank system, but a much larger scale. There wasn't obviously enough water to do toxicity on these, but they looked at constituents over time in these in the saturated zone. And on to riverine and lacustrine systems. So this was the wave tank experiment that was carried out at CanMet as well. And these were disrupted, I'll say, by COVID. There were several experiments taking place at the same time that were cut midway, and it caused a lot of delays. So COVID definitely had an impact in this project. There was a lot of experiments that we had to repeat over and over again because they were stopped. Anyway, so 20 roughly liters of dilbit added to a wave tank experiment to mimic wave action and natural weather. And here carried out in collaboration with researchers at Experimental Lakes area and by Ottawa U. So I'll just point out, of course, for the experiments carried out at CanMet and this experiment at the ELA, this wasn't paid for by our project. We just carried out analysis because our budget wasn't that big. So in this case, they went to the Experimental Lakes area and they built these windmill corral systems, and they dumped a bunch of dilbit at very high concentrations. And we analyzed the PLFAs and the carbon 14, carbon 13 values in PLFAs in sediments to see what, if dilbit was being utilized as a carbon source by microbes. That's just up close, the windmill corral. So main findings, shallow groundwater systems. The biodegradability of dilbit was similar to that of conventional agriculture over 104 days in the unsaturated zone. Despite higher concentrations of petroleum constituents in dilbit contaminated leachate, there was no significant differences in toxicity between dilbit and conventional agriculture in the unsaturated zone as well. And despite declining concentrations of petroleum hydrocarbons, toxic effects only became evident beyond 42 days. And that was I showed you from the large tanks. Surface weather experiments. So oxidized degradation products likely contributed to the consistently sublethal toxicity of weathered crude oils over the 56 days. I haven't shown that, but so similar results in the freshwater systems. And in terms of what we saw in the windmill corrals, there was actually no significant microbial uptake of dilbit-derived carbon. So they're using a more modern carbon source. So that has implications for dilbit spills in freshwater systems and lakes like that. So one recurring theme that we found in all our experiments was that there's unidentified petroleum constituents. So particularly polar organics within the water-soluble fraction that contributed to toxicity. So future work should aim to better identify what particular oxidized hydrocarbons or other species were responsible for toxicity. Thank you.